So good evening, everyone. Welcome to all of you for today's seventh live session on MATLAB based programming lab in chemical engineering. So this is my introduction. I have completed my BTech from NIT Surat in 2019. Then I joined Reliance Industries Limited at Jamnagar and I worked there for a year. Uh, Mostly I learned there how to use S Pen Plus software with real world problems. Then I completed my master's from IIT Kharagpur in 2022. There I learned a similar course on MATLAB from Professor Parag Deshpande. Currently, I'm pursuing my PhD from IIT Bombay. These are pages from where you can connect me, and this is the YouTube link where all the recorded videos of live sessions are uploaded. So today we will be learning how to solve simultaneous ordinary differential equation. So before going to these difficult problems on chemical engineering, we will first see some easy problems, some questions from previous year's assignment, and we'll first try to solve them. So just a minute. Sorry, I've by mistake closed it. Okay. So we will solve these problems. So today's first problem is consider an autocatalytic reaction system in a batch reactor. A is converting into B, that is a slow reaction with rate constant is equal to K1. Second reaction from this B, so 2B are getting converted into C plus some unreacted B. And again, this B plus C is going to A plus C. So these two are very fast reaction and this A to B is small reaction. Second reaction is very fast and third reaction is just fast reaction. So the rate of reactions are given as dCA by dt is equal to minus K1 into Ca plus K3 into Cb into Cc. From here we can understand dCA by dt, A is getting consumed, so it is minus K1 Ca, and in this reaction A is getting formed, so plus K3 into Cb into Cc. Then dCb by dt is equal to, here B is formed, so K1 Ca, here minus K2 into Cb square, and here minus K3 into Cb into Cc. And dCc by dt is equal to Kv K2 into Cv square. So these are the rate of reactions. Rate equations are given to us. The initial conditions are at T is equal to 0, Ca is equal to 1, Cb is equal to 0, Cc is equal to 0. So we are just starting with initial concentration of A, that is 1 moles per meter cube. The rate constants are K1 is equal to 0.05 second inverse, K2 is equal to 2.5 into 10 raised to 7 meter cube per mole per second, and K3 is equal to 1.5 into 10 raised to 4 meter cube per mole per second. So meter cube per mole per second, that is the unit for second order reaction. To analyze the stiffness of this problem at T is equal to 0 or at initial conditions, choose the correct second norm of the Jacobian matrix. So Jacobian matrix, we have learned how to calculate Jacobian. So I will not repeat it for this lecture. So we are supposed to find norm of this Jacobian matrix and second norm. So what is second norm? We will learn it. So, okay, let's try to solve this problem. I hope my screen, everything is correct. Yes. So let me first write down the equation from here. See, okay. So our equation is, I will just write first equation is minus K1 into Ca plus K3 into Cb into Cc. Then second rate equation is K1 into Ca minus K2 into Cb square. This is my second rate equation. And my third Rate equation is minus K3 CB into CC. Here there is one more term, minus E3 into CB into CC. Okay. And our third equation is K2 into CB square. K2 into CB square. So we have total three equations. Now, first, to find the Jacobian, we will have to use our symbolic tools. So I will use sims, sy, ms, and I will just write down all these values CA, CB, CC, then K1, K2, and K3. Correct? Now we have to find a Jacobian. So first we will have to add our matrix. So these three equations are in three different rows. So this first row is first equation, second row is second equation, third row is third equation. So I will write down my matrix F, that is equal to this first term minus K1 into CA plus K3 into CB into CC. So this is my first equation. I will put one semicolon. Then my second equation, this huge equation. Okay. And I will put one semicolon. We will go to next row. And this third equation. Let me increase this if I can. Yes. This is my third equation. Okay. So I have written down my matrix. Now, what do I need to find? I need to find a Jacobian. So let's say J is equal to Jacobian of matrix F. Okay. So it won't work like that because we have. Okay, let's run and see what happens. It won't work. Why it won't work? Because we need to say what are our variables. So our variables we need to find with respect to CA, CB and CC. Now it will work. Oh, again it's showing an error. Error on which line? This line. Minus K1 into CA. Okay, it is showing error in line number 10. As far as I am understanding. This is our first row, second row, and third row. We have used SYMS, CA, CB, CC, K1, K2, K3. Yeah, here, okay. I need to give this. Okay. No, it is again showing the error. It should not show this error. A2 into CB square. Correct? And this Jacobian is Jacobian matrix of F with CA, comma CB, comma CC. I don't know why this is the correct format to calculate Jacobian. We use symbolic math tool CA, CB, CC, K1, K2, K3. Then we write down our Jacobian matrix. Okay, let me do one thing. Okay, before going to here, let me check what is actually happening here. Is this the issue at this line? Okay, so we have written K1 into CA plus K3 into CB into CC. Okay, Let me write down here in command window. Let's try to understand what is the issue. Dimensions of objects being concatenated must match. Okay, so it is some issue with dimensions. Okay, yeah. No, but it will not give us three cross. I guess there is some issue because this is the way we calculate. This is the way we calculate our Jacobian. It is not taking it as this row matrix. I am not understanding it why. It is some space issue. Yeah, it was some space issue. Okay. So see, this is our matrix F. We have write down our equations. Now I will find, okay, so what is the issue if you are giving some space here? So it is taking this term as some different row. So be careful while you are dealing with Jacobian. Just don't give anywhere any space. Okay, now I will find Jacobian, that is J is equal to Jacobian of matrix F with respect to CA, CB and CC. Okay, and see what are we getting. Okay. So our Jacobian matrix is coming out to be minus K1, K1 0, CC into K3 minus 2CB into K2 minus CC into K3, 2CB into K2 and these three terms. Okay, now what are our initial conditions from problem statement? Let's write them down. So our initial condition are CA is equal to 1, CB is equal to 0, CC is equal to 0. Okay, CA is equal to 1, CB is equal to 0 and CC is equal to 0. Okay, if I put down these three values, this term is CC, this is 0, CB, CC, this whole column 2 and column 3 both are 0. So we have only column 1, that is minus K1, K1, 0 and all other terms are 0. So what is the value of K1? Value of K1 is 0.05. So K1 is equal to 0.05. So what will be my new J Jacobian matrix? J with value will be equal to my Jacobian matrix with value will be equal to minus K1, that is minus 0.05, 0, 0. Next column 0.05, 0, 0 and last row that is 0, 0, 0. Okay, now what I am supposed to find? I am supposed to find a norm, second norm. So let's first understand what is norm. Why is it written second norm? So there are some other kinds of norm also available. Okay, I'm muting you. Okay, so there are three types of norm: norm 1, norm 2, and P norm. Okay, so what is norm? Okay, what is one norm? So when I want to calculate one norm of matrix minus 2, 3, minus 1, so it will what it will do? It will take absolute value of each entry and add it. So this is minus 2, 3, minus 1. So what is the norm 1? It is mode of minus 2 plus mode of 3 plus mode of minus 1. That is coming out to be 6. Norm 2 is norm 2 between two vectors. It is just difference between two vectors. The way we used to calculate square distance between two vectors, that is norm 2. And there is one uh, infinite norm. Yeah. Okay. So we just need to find a norm to. Norm to means distance. So what I will do, norm of matrix J I will calculate. So this norm of J underscore value, I need to report that value. So that is coming out to be 0.0707. So from the options available, 0.0707 is norm J. So from here, what did we learn? We learned how to use Jacobian function and what kinds of norm are available. So, okay, let me give you some theoretical background of norm 1, norm 1 and norm 2. We will not use ChatGPT as of now. Okay, so what is norm 1 and what is norm 2? So norm 1 is just if it is available here. No, it's not available here. Okay, let me just show you by my own way. So here, let's say I'm writing one matrix E is equal to 2 minus 5 2. So what should be norm 1? Norm 1 should be come out as norm of A. If I will just write norm of A, it will give me distance with respect to 0. But I want to calculate norm 1. So what it will give me? It will give me absolute difference between this matrix and it will consider one 0 matrix. And it will just 2 minus 0, minus 5 minus 0, 2 minus 0, and it will take absolute value of each values. Let's say I want to A is this and B is 1, 2, 3. So what should be my norm 1? It should be 2 minus 1, 1 plus minus 5 minus 2 minus 7. So plus 7, 3 minus 2, 1. So like that I can calculate norm of A minus B and first norm. So see, it gave me 9. If I want to calculate norm 2, I'll just write norm of A minus B. I want to calculate norm for A minus B like that. Okay. So this is the way we can calculate norm. Norm is nothing but it gives how far those 2 points are. Okay. So let's move it with the next question. It is preferable to use number of CSTRs in series to achieve a specific conversion than a single CSTR for same inlet flow rate and concentration. Is this correct? Let's say I am having one feed condition F and my initial concentration is CA0. I want to achieve specific conversion. So what I can do, I can use one simple or one single CSTR, or I can go for a multiple CSTR. So from your chemical reaction engineering's class textbook that Levenspiel, you know that when we go for series of CSTR, the total volume of CSTR is less than the single volume of CSTR. So what is the sentence? It is preferable to use a number of CSTRs in series to achieve a specific conversion than a single CSTR. Okay, so it is always preferable, correct? So answer is true. So we should always go for number of CSTR in series compared to one single CSTR. So it will save our volume of CSTR. Okay, our next question, a simplified model for the growth of flame can be expressed by the following ordinary differential equation, that is dz by dt is equal to z square minus z cube. Here z is the height of the flame. After ignition, the flame grows very fast to reach a critical size where it remains thereafter. So what happens when flame is ignited? It grows, that length grows very fast, and after some time it reaches to some critical size of the flame where it stays. You may have observed this. The initial condition is z is equal to 0. Z of 0 is equal to 0.01. So when t is equal to 0, z is equal to 0.01. Determine the time requirement to reach the maximum flame height if the system is studied up to 150 seconds. And we are supposed to use ODE 15 inbuilt solver. Okay, so first let's search for this ODE 15 solver. ODE 15. this ODE 15 solver. So what is its this syntax? T comma y. So if I'm writing dy by dt, so it should be t comma y is equal to ODE 15s in bracket my function, then time span and my initial conditions. So see, if I want to calculate dy by dt is equal to minus 10t. So I need to first write down ODE 15s is equal to at the rate t comma y minus 10 into t, my equation, then comma t span 0 comma 0 to 2 and my y0. Okay, so similarly, let's try to solve this problem. Okay, we are given as, I will just, okay, let me go for new one. I will write down clear all, sorry, clear all CLC. Okay, so here we are given, I will write down that equation in comment, dz by dt is equal to z square minus z cube. And we are given initial condition of z of 0. This means that t is equal to 0, z is equal to whatever the value is given, that is given as 0.01 units. So this is z of 0. And my next condition, where our time span is up to 150 second. So our t span is t is equal to 0 to 150 we are supposed to study. Okay, so let's try to write it down like this way. Yeah, this I want to write it down like this way. So my function f is equal to at the rate of t comma z, correct? Or z comma t comma z. What is my equation? Z square minus z cube. This is my equation, z square minus z cube. Now I will use my ODE solver. So how do we write it down that? See here, in bracket t comma y, t comma y is autocorrecting, t comma y is equal to, okay, what is our function? Function is ODE 15. We are supposed to use ODE 15s. ODE 15s. ODE 15s. What is my, the way we write down it here? My function, that is f, comma. First, I am supposed to give t span. So what is the value of t span? 0, comma 150. And what is my initial condition? It is 0.01. So let's first try to solve this and see what we are getting. Okay. So for particular values of t, we have particular values of y. Okay. But what we are supposed to say, determine the time requirement to reach the maximum flame height. So what is my maximum flame height here? Is this a good way to check here, or we should plot it? What should we do? We should plot it. Okay, here it should be t comma z. It doesn't matter. Okay, so let's plot it. So plot on x-axis, it should be time. On y-axis, it should be flame height. Okay, I will just run this. Okay, so okay, this is the plot that I am getting. So I will open it in new tab. So see here, this is my maximum height around here, somewhere around here, somewhere between 100 to 110. I am getting a maximum. So what is the options that those are given to us? Okay, no options are given to us. So what will be the times? The time will be something around 110 seconds. Correct? So the correct answer is answer C, that is around 100 seconds. So how can we make this plot even more better? What can we do? So We can give some axis label, like using X label command. I can give time. I can mention in which unit time is given. So it is in second. Y label. What is Y label in flame height? We are not given any units of flame height, so I will just write down flame height. Okay. What I can further do, I can change the color of this thing. I can, let's say I want to give it in K. K means black. Okay. So this is how we can improve our graph. We can also give chart title. So see, let's say I want to give a chart title. So I can give title. What should be my title? Variation of flame height with time. Variation of flame height with respect to, okay, let's just write WRT with respect to time. This is what I can give a title. See, we can also add line width. So I don't remember that command. So let's search how we can add or we can change this by default line width plot. Let's search it in that way. Okay, so here I can change that line width. If it's shown here, we can learn. Okay, let me simply do Control F and then width WIDTH. Yeah, okay, specify line width here. So see here, line width 2. So let's try it here also, comma, line width 2. So see, it is bit darker. So this is how you can improve your visibility of your log. So this was the problem where we learned how can we use ODE 15. Okay, let's do one thing. Let's keep these on hold. I am here writing T1 comma Z1. Now I want to use further more command that is ODE 23 and ODE. Here what, which one ODE 45 we have used? So let's use ODE 45. Let's say T3. T is same for all cases. So I will not change T. Z3 and Z2 ODE 23. So now let's say I want to plot this thing. So how can I do? I can now press one hold on command, and by hold on command I am holding my plot. So here I can add Z2. Let's say I'm keeping it B. B with B meaning blue. Further hold on, and let's say I'm again adding it with Z3, and let's say I'm calling it green. So let's see, are we getting any changes? Okay, so here time matrix is not same for all the cases. That is the issue. Let me do T1, T2 and T3. I assume that it is same, but it is not. T1, T2 and T3. I guess it will not work. Yeah, see, it worked. So it is opening in new command window. So this green. Okay, so how can we understand which one is which line? So what should we do? We should add legends. So I will add legend here by writing legend. First one is ODE 15 S. Then second one is ODE 23 and third one is ODE 45. Okay. So we will be having legends Okay, so ODE, we can clearly see that ODE this ODE 23, see ODE 15 is somewhere coming out, but ODE 23 and ODE 45 are more or less in this region. If I zoom it, so there is some significant difference slightly in this region. Else ODE 45 or ODE 23 are more or less doing same work. Okay, so this is how we can solve ordinary differential equation. Okay, let's move ahead with this. So what did we learn from this problem? We learned how to use inbuilt ordinary differential equation solvers. Okay. So next question. Okay, so what are we having now? We are having two ODEs in series. So consider the following set of ordinary differential equations and solve it using ODE 45 solver. dy1 by dt is equal to minus 0.08 y1 raised to 0.5 minus 0.1 y2 raised to 0.2. Second equation dy2 by dt is equal to 0.1 y1 raised to 0.2 minus 0.16 y2 raised to 0.3. Okay, so let's try to solve this equation. So for this equation also we will need one MATLAB function. Okay. So let's write down first function. So we will write down function separately. So here it was in question, it was here only where we defined f is equal to this. But here there are multiple equations. So it is better if we define it below. So I can write it down as function. Okay, let me first write down my equations here. So first equation is dy1 divided by dt is equal to minus 0.08 into y1 raised to 0.5 minus 0.1 into y2 raised to 0.2. My second equation dy2 divided by dt is equal to 0.1 y1 raised to 0.2, 0.1 into y1 raised to 0.2 minus 0.16 into y2 raised to 0.3. So these two equations I want to solve. So I will write down my function. Let's say I am calling it dy. dy is equal to name of the function. Let's say ODE and it is t comma y. I will give my input as t comma y. So my first equation. So I will write down dy 1 comma 1 is equal to minus 0.08 this thing. But here we don't need to write y1 and y2. We need to write y of 1 and y of 2 because we have just given y in vector. Okay, so here also y of 2. And my second equation is 1. Okay, so what I have done, I have defined my function. I will place one end. Okay, so let's write down our initial code. So what is the value of time span given to us? We are supposed to find at 10. So let's say my time span t span is equal to 0 and 10. And what I need to give? I need to give initial conditions. So we have a matrix. We have two equations. So we'll have two initial conditions. So for first equation, what is the initial condition? T is equal to 0, y1 is equal to 0.95. And for second equation, the initial condition for y2 is 0. Okay, so I have given my initial conditions. Now I will use my solver t comma y. T comma y is equal to ODE 45. We are supposed to use ODE 45. Okay, what is the name of my function? I need to place one at the rate and I need to write down what is the name. Name is ODE. Then my time spent, T span, comma my initial condition, that is y0. Okay, let's try and run it. Okay, so we are having T1, T2, yeah, we are having T span and values of y. Okay, so now what are we asked? Y2 of 10. So last this thing. So why do we see it from here? What is y2 of 10? Let's say y2 underscore 10 is equal to y of which row? Last row. I will put this and sorry and second column. So my answer is 0.310 minus 0.000 I. So 0.000 I is nothing. It is no imaginary number. It is 0 I. So our answer is real number, that is 0.0310. So 0.03 is my answer. Okay. I just want to check one more thing. If I just write dy of 1 and dy of 2, will it work? It will not work because we have two inputs y1 and y2. So that's how we need to write it like this. Okay. So we are done with this problem. So we have estimated initial condition. What further we can do? We can plot this, right? So let's try to plot it and see what is happening. Okay. So I will plot. Okay. So before plotting, let me do one thing. All rows and first column. Okay. All rows, every row and my first column is y1. So I will just write it down it as y1. And similarly, my all rows and second column, I will define it as y2. And let's now plot it. Plot t comma y1 comma, let's say I want to keep it black with line with line width of 2. I will press hold on. I will again y2. Let's say it is green. Let's say it is blue. Okay, then we will use uh, what are we supposed to? Yeah, X label. X label. Let's say it is T. Let's say Y label. Y label. It is Y. And I'm not willing to give chart title for this problem. Let's say I'm giving legend. So my first legend is y1 and my second legend is y2. And let's now run this. Okay, there is some error. X label, okay, label. Okay, and let me just put one semicolon here because it is every time printing that I don't want to see. So you remember it was 0.000 I. So they are writing that we are ignoring this. So see for both the equations, we are getting one exact solution at some this point. And this y1 is also decreasing function, y2 is slightly increasing, and then again decreasing. If we go for a longer period of time, let's say I'm going from 20 to 30, 40, let's say it's 40. Is it steady state or not? We don't know. So let's try to see that. This is not, this is continuously decreasing while this is first increasing, then decreasing, and then slightly increasing. Okay. So this is how we can write down our function and we can define it below the file, below or at the end of the file. Okay. So now let's take the next problem. So answer of this problem is 0.03. Okay. Next question. Oh, big question. One mechanism of deactivation of solid catalyst is by parallel reaction, in which the reactant produces a side product which deposits on the catalyst surface and deactivates it. Okay, so this is the common phenomena when we are dealing with process of solid catalyst. In a catalyst, in a catalyst loaded batch reactor, the rate equations are for the reaction and catalyst deactivation are this: minus dc by dt for catalyst, that is k1 into c raised to 1.5 into a, and for catalyst deactivation, that is minus dA by dt is equal to k2 c raised to 1.2 into a square. So here A is the activity of the catalyst palette, C is the concentration of reactant, K1 is the modified reaction rate constant, and K2 is the rate constant for catalyst deactivation. Given K1 is equal to 3.5 into 10 raised to 2 some units, K2 is equal to 1 into 10 raised to 2 into some units. The initial condition is at T is equal to 0, we will have some uh, concentration. So C is equal to 100 and our activity will be equal to 1. What is the value of A at T is equal to 5? Okay. So we are here again, we are having some series of differential equations. So I will use clear all CLC. For the first equation, I will write it down as minus dc by dt is equal to k1 into c raised to 1.5 into a. And my second equation, we are currently looking at problem number 5, right? Okay, let me just do one thing because I am going to save all this problem somewhere. So let me write it down here as problem 1, control A, control C. I'm going to save them notepad, control V. Then, okay, I will deal this with later. Okay, so here dc by dt is this term. For my second equation, minus dA divided by dt is equal to k2 into c raised to 1.2 into a square. Okay, so let's first write down one function. So same thing we will do, function dy is equal to, let's say I'm giving the same name ODE t comma y. My first equation dy of 1 comma 1 is equal to minus of this term. I guess we will not be able to write C1. We will write it down C1. Let's say, okay, here we need to give the values of K1 and K2. So K1, what is the value of K1? K1 is equal to 3.5 into 10 raised to 2. So 3.5 E2, and K2 is equal to 1 into 10 raised to 2, that is 100. Okay. So my, let's say my C1 is equal to y of 1 and my a is equal to y of 2. I can also define it here or I can write it down the way I have written. So this is my first equation. So this term dc by dt, and my second equation 2 comma 1 is equal to minus of a2 into c raised to 1.2 into a square. Sorry, a square, and I will press one and as I need to close the function. Okay. Okay, now let's define our time span. What is told? Is there anything after 5 minutes? Okay. And here, if we see the value of k1, it is in terms of hour inverse. So what I need to do, I need to convert my time into seconds. So 0 is 0 and my second is 5 minutes. So it will be 5 divided by 60 hours. Okay, this is my time. Then my initial condition y0, that is equal to first equation for value of c, it is 100. And for second equation, value of a is 1. Correct? Now let's say t comma y is equal to ODE 45 at the rate. My function is ODE. I have t span and I have y0. Okay. Okay. So what are we asked? What is the value of a after at t is equal to 5? So what will be the value of a? Okay, let's first run it and understand then. Okay, there is some issue in. Okay, here it is. Let's not define C1, it is just C. Oh, I need to put semicolon here because every time it is printing out everything. So here, this is C and this is A. So what is activity at last time? This one and this one. So 101th row or end row and second column. So what was that value? That value was 0.0018. So my activity is significantly reduced from 1 to 0.008 within 5 minutes. Okay. So what we can do, we can plot this. Let's say C is equal to y of all rows and first column, and my activity is equal to y of all rows and second column. Then I will plot first time comma C comma same thing. Let's say it is I'm giving it black. I'm giving it black, so that is K, and then line width of 2. Then I will put hold on plot t comma a comma, let's say it is green, then line width of 2, and let's say x label is my time, y label I'm just giving it some value, I'm just writing it as value, and we need to give legend. So first legend is C and second legend is A activity. Okay, so now let's try to run this problem. So C activity. Okay, so this concentration value is really large, that activity is not showing any change. So let's do one thing. Let's plot them in separate figures. So let's say this is figure 1. I guess here we don't, if we don't put hold on, it will, for live script, it will show two different scripts. So see, here this is concentration and here this is activity. Activity is significantly reducing. Okay. So let me do one thing. Let me save this to here in my this is assignment 7. New A7. This is our problem number 5. Right, pro 5. Okay. So this I don't need it now. So this problem also I will save. Problem number 4. Just give me a minute. Control S. This is pro 4 and this is pro 3. Oh, this was pro 1, not pro 3. I will have to rename it. I guess it will not work because it is open. Okay, so let me just close this. That is problem 1. C, problem 1. And this one is problem 3. Control S, problem 3. Okay. So now let's move. So till now, what did we learn? We learned how to write down, how to define a function at the end of the file. Then we learned ODE 45, ODE 23, and ODE 15 as solvers. So let's move ahead with the next question. If someone has joined, so if you are having any doubt, I don't know how to pronounce your name, but if you are having any doubts, please feel free to ask me. So we'll move ahead with the next problem. Okay, so transient behavior of a system is described by the following ordinary differential equations. Those are dy by dt is equal to minus yz plus epsilon gamma z. This is gamma not y. And second one, epsilon dz dt is equal to y minus yz minus epsilon gamma z. And we are given y of 0 is equal to 1 and z of 0 is equal to 0. Epsilon is equal to 0.01, gamma is equal to 5. How does z vary from time 0 to 1? Okay, so let's write down our equation first. So my first equation is dy by dt is equal to minus y minus yz minus it's plus epsilon gamma z. So I will write it down as with plus epsilon gamma z. This is my first equation. In my second equation, so see, second equation is epsilon is here. So what I will do, I will write down dz by dt is equal to my whole equation. I will just copy this. That is y minus yz. Here it is minus epsilon gamma z and whole term divided by a constant that is epsilon. Okay, so let's do one thing. Uh, let's first write down function dy. is equal to ODE t comma y. Then my first equation dy of 1 comma 1 is equal to, so I can define here separately y of 1, y of 2, or I can do it on top. So let me do it on top. Let me first define what is epsilon. Value of epsilon is given as 0.01. Value of gamma is given as 5. Yes, and let's say my y of 1 is equal to y, and y of 2 is equal to z. I don't know if it will work or not. Let's define in terms of x and okay. Here let me write down x, not z. So x of 1 and x of 2. Okay. Now my second equation is the same equation. Okay, and I will place one. Okay. So here, okay, what is the time span given to us? Time span is given to us from 0 to 1. So t span is equal to 0 comma 1. Then initial guess, let's say y0 is equal to, what is the initial guess? For the first equation it is 1, for the second equation it is 0. So 1, 0, and I will use t comma x. Let me write t comma x to avoid that y terms. So t comma x is equal to ODE 45 at the rate ODE comma t span comma y0. Okay, let's first solve this and see what is asked. Okay, so how? Okay, we are supposed to use ODE 15s, not ODE 45. Okay, I have somewhere defined y. Okay, x of 1 mean I'm assigning at y. So I need to write it down like this. Now like this. Okay, and we are supposed to. Okay, here there are some errors. I'm supposed to go to 50s. Okay, we are facing some errors. So let's try to see the last problem, the way we solved. And let's try to replicate it. And let's try to understand what mistake we are doing. I don't know why it is showing. Let me just write down E if it is fine. It must return a column vector. Okay, so here we are having some issues in function. Yeah, okay, this thing. I guess it is this because of space, the way we face the issue in the first problem. Okay, now it will be resolved. Okay, so now let's try to run it. No, again it is showing an error. I'm not understanding what is the issue. Okay, we are facing some error. I'm not understanding what is it. Oh, here it should be 2 comma 1. Sorry, that's why. It is first row, first column, second row, first column. Okay. So I by mistake wrote it down 2 2. So that's why it was error. So let's try to see. Okay, what is the problem statement? How does Z vary? So let's plot Z. So my first term is Y and second term is Z. So I will write down Y is equal to X of all rows and first column, and my Z is equal to X of all rows and second column. Then I will plot. First, let's plot both. Y on x-axis it is time, y-axis it is y, comma same thing. Let's say it is black with line width of 2. I will put one hold on. Say plot t comma z comma let's say it is blue. Sorry, this auto correcting. Blue comma line width 2. Let's say x label is my time. Y label I'm just writing it as value, and we need to give legend. So legend, first legend is Y, second legend is Z. And let's try to run this and see what we are getting. So we have 4 options. Okay. Yeah, okay. We need to give legend in this way. Okay, now let's try to run it. Oh, it is T span, not just T. So I need to write down here T span. Or let me just remove it. I don't know why it is showing this kind of plot. We have made some mistake. Wait. Okay, here, this is the issue. Yeah. Please be really careful while you are writing. These small mistakes can cause issues. So here what is happening, Z is first increasing, then decreasing, and Y is continuously decreasing. So let's see our options. First option is Z increases in the beginning and then decreasing. So Z increases in the beginning and then decreases. So option A is correct. Option 2, Z increases throughout, that is wrong. Option C, Z decreases throughout, that is also wrong. And option D, Y increases throughout. So Y is decreasing throughout. So our correct option is only A, Z increases in the beginning and then decreases. Okay. So let me save this problem. Okay. Is it saved or not? Wait. Oh, I have just saved the data. Wait. I don't want to see the data. Let me delete this. This particular control S I need to. Yes, yeah. Now it is MATLAB live code. Problem 6. Correct. Okay, let me do one thing. Let me change my folder from here only. So it will automatically save my codes here. Okay. So I hope everything that I have taught till now is clear to everyone. Let's move ahead with next problem. Problem 7. I hope whoever has joined, if you are having any query, please feel free to stop me and ask me. Okay. So my next question, we will move ahead with problem 7. It says that consider the following system of linear ordinary differential equations. Dx by dt is equal to y. Dy by dt is equal to minus 2x minus 3y. The initial conditions are at t is equal to 0, x is equal to 1, and at t is equal to 0, y is equal to 3. And what is the value at t is equal to 10? Okay, so same thing. I am repeating these exercises. I will first write clear all, then CLC. Okay, then I will write down my first equation, that is dx by dt is equal to y. And my second equation is dy by dt is equal to minus 2 into x minus 3 into y. Okay, so let's write down a function dy equal to ODE t comma y. My first equation, two. Okay, so here also we need to define, or okay, let's here instead of defining, let me just write down as y of 1 and dy of 2 comma 1 is equal to, okay, no, it is y of 1, not y of 2. Okay, now I will press on end. My time, what is the time given to us? Time given to us is from till 10. So I will write down t span is equal to 0 comma 10 and initial conditions. So let's say y0 is equal to first equation t is equal to 0, x is 1, and second equation it is 3. So 1 comma 3. Okay, so let's write down t comma z is equal to ODE. What are we supposed to use? OD 45. OD 45. I'm sorry. ODE 45 at the rate ODE comma T span or just T, no, T span comma initial condition, that is y zero. Let's first run this. Okay, so I have Z matrix. Now, what are we supposed to say? Value of x at t is equal to 10. So x is my first row and t is equal to 10, last column. Sorry, first column and last row. So it is really a small number. 2.275 into 10 is to minus 4. 2.275 into 10 is to minus 4. So our correct answer is answer A, option A, 2.275 10 is to minus 4. Let's further try to plot it the same way that we did. I'm sorry, just give me a minute. Okay, so let's further try to plot our data. So, okay, so my X is Z of all rows and first column, and my Y is equal to Z of all rows and second column. Okay, then I will plot t comma x. If I do it like t comma x comma y, and let's see what is happening. No, it won't work. See black, same thing. Line width, let's say it is 2. Hold on, plot t comma y comma, let's say blue, with line width of 2. X label, it is time. Y label is some value, and legend, first legend is X and second legend is Y. And let's try to plot it. Oh, so see, this is how plot looks like, but we are supposed to say just x equal to 10. So from both X and Y are nearly same at X is equal to 10. We can also see from here both X and Y are nearly same, but in opposite directions. Correct? One is below and one is above. Okay, so let me save this problem. 7. Okay, I hope everything is clear. Now, let's move ahead to the next problem. Consider the following system of ordinary differential equations. dy1 by dx is equal to minus 1.2 y1 plus 1.5 y2. dy2 by dx is equal to 40 y1 minus 190.3 y2. Given y1 is equal to y1 at x is equal to 0 is 1 and y2 at x is equal to 0 is 0.1. What is the value of y1 at x is equal to 100? And we are supposed to use ODE 15s. So let's try to solve this problem in the same way. Yeah. Okay. So let me write down the equation. Just give me a minute. Okay. Let me write down the equation dy one in comment part. So dy one divided by dx is equal to minus 1.2 into y1 plus 1.5 into y2. Okay, similarly, my second equation is dy2 divided by dx is equal to 40 into y1 minus 190.3 into y2. Okay, So let me write down my function the way similar with the way we are doing it. These questions, this kind of question are supposed to be there in your exams. It's equal to y. So my dy of first row, first column is equal to my this equation. Or let me do one thing. Y1 is equal to y of 1. Y2 is equal to y of 2. Okay. So I just don't need to modify anything. Okay. I will press one and. Okay. So now in problem statement, what is told to us at x is equal to 100. So my t span will be, or let's write x span is equal to 0, comma 100. And my initial gas y0 is equal to, okay, what is my initial gas? X is equal to 0, y1 is equal to 1, and x is equal to 0, y2 is equal to 0.1. Okay, this is my initial gas, and I will write it down as t comma y is equal to, what are we supposed to use? We are supposed to use ODE 15s at the rate ODE comma x span comma y0. Okay, let's first try to solve this and see what we are getting. Okay, so we have solved it. So see, these are the values of y1 and y2. Okay, so now let's see what is asked. Y1 at x is equal to 100. So x is this, y1 is this, and x is equal to 100 is last. So it is 1.1414 into 10 raised to minus 11. And what is asked in question? Correct to the nearest integer. So what is the nearest integer for this value? That is 1.1414 into 10 raised to minus 11. That is nothing but 0. So let's do further exercise of plotting. Y1 is equal to first column and y2 is equal to y of all rows and second column. Okay, and my, okay, plot x comma y1 comma um, let's say blue line width of 2. Hold on. Let's say I'm putting yellow, so it is y comma 2. Let's say x label is my x, y label is my y, not y, okay, y, and legend is y1 comma y2. And let's see how our plot looks like. Okay, there is something unknown. Okay, here t comma y. So instead of t comma y, I will write x comma y. See, both are approaching the same values. It is looking like this from here, but if we go for the values, maybe one is positive, one is negative, or both are at same signs. No, their approach is same. See, this one in both are going in same signs. Okay. So this is how we can. So from these exercises, what we have learned solution of simultaneous ordinary differential equations using ODE 15s tool, ODE 23 and ODE 45 tool. Further, we learned how we can use plotting tools and how we can use plotting tool and how we can improve the visibility of our graphs. Okay, let's move ahead for some theoretical questions. The question is, a reaction occurs in a vessel such that the total reaction mass does not change with time, but its temperature increases. The system is at steady state. Is this true or false? This is absolutely false. So what is steady state? What is the definition of steady state? So when the system is at steady state, all properties, all properties with respect to time does not change. All properties like temperature, pressure, mass, nothing should change with time. That means it is in steady state. But here, what is the problem statement saying? A reaction occurs in a vessel such that the total reaction mass does not change. Okay, reaction mass is not changing with time, but its temperature is increasing. This means that temperature is not constant with time. So is this process steady state? No, we can't tell this process steady state because everything should remain constant or it should not change with respect to time. So our correct answer is false. The system is not steady state. The system is unsteady state. Okay, unsteady state. Okay. Okay, let's move ahead with the next problem. Consider n equal sized CSTRs connected in series for carrying out first order reaction. The initial concentration is C0, residence time is tau, rate constant of the reaction is K. The concentration at the outlet of nth reactor. Okay, so for first CSTR, I can write Ca minus Ca0 equal to, or C1 minus C0 equal to A into C1 into tau. Okay, so no, it is this C0 minus C1. Let's C1. So C0 is equal to C1 into 1 plus K into tau. So C1 is equal to C0 divided by 1 plus K into tau. This is for my first reactor. Okay, for second reactor, what can I write? C2 is equal to, or let me write it down. C2, sorry, C1 minus C2 is equal to K C2 tau. So I can write C2 is equal to C1 divided by 1 plus K into tau. And what is my C1? C1 is C0 divided by 1 plus K tau. So 1 plus K tau square. For second reaction, it is 1 plus K tau square. So what will be the outlet for the nth reactor? So Cn will be equal to C0 divided by 1 plus K tau raised to n. Okay, so our correct answer will be this, or this. Our correct answer is option 1. Is C0 Cn is equal to C0 divided by 1 plus K into tau raised to n. Okay, let's move ahead with the next question. The mass flow in and out of a steady state process are both increased by 10 kg per second. What will be the accumulation? Okay, so how can I write accumulation? I'm just writing A. Accumulation is equal to rate in minus rate out. Okay. So now what I am doing, both I am increasing by 10. So rate in plus 10 minus rate out plus 10. So it is nothing but what we are getting at initial, rate in minus rate out. Okay. But what is told, the system is non-reactive. So that's why we have not added that formation or uh, formation term or disappearance term. So what is told initially of a steady state process. So for steady state process, this is already 0. So our answer is this A, that is 0. Okay. So this is how we can write down mass balance and we can solve this. Okay, now let's move ahead with the next question. Unsteady state mass balance of dynamic CSTR is, what is unsteady state mass balance? So what should be first? Rate of in. In meaning rate of addition. Minus rate of removal or rate of disappearance plus rate of formation will be equal to V into dc by dt. So this should be equal to this dc by dt term. So this option is saying rate of total amount in the reactor, wrong. Total amount, no. It should be some rate. So it is time rate of total amount in the reactor. It is this thing, time rate of total amount in the reactor. Okay. So our correct answer is A, time rate of total amount in the reactor. Now next question. There is no axial mixing in the plug flow reactor. So this is plug flow reactor. So fluid is moving like this, so it should not mix axially. Correct? So this is true. Okay. So the next question. Wait, I have not saved this problem. Problem 8. Okay. So my next question is, which of the following is true for a reaction occurring in batch reactor? So in batch reactor, we dump everything, then reaction starts and we dump out everything. So for batch reaction, rate of accumulation is equal to minus rate of disappearance, right? Our actual balance is in minus out plus formation is equal to accumulation. But in batch reaction, there is no input, there is no output. We just dump everything. So what should be there? The accumulation term is 0. No, this is wrong. Only reactant term is 0. Only reactant is not 0. Both product is also 0. So this is also wrong. Only product term is 0. Wrong. Both the reactant and product terms are 0. So this is the correct answer. Next question. What happens if we don't stop the implementation of hold function? Okay, nothing happens. It is not like that. No error is going to generate, plot function is not work. It's not going to happen. This will happen. What hold? Hold means it will keep on hold and it will adding the cows. So MATLAB keeps on adding the cows in the same plot window. So this is the correct answer. So this is all for today's assignment part from the last year's assignment. Now let's try to take some problems. Okay, so we will see this first problem. Just give me a minute. So the problem statement is this: continuous stir tank reactors in series. No series reactions in a CSTR. So consider a system of elementary reactions in the series of type A to B to C. The kinetics of the system is given by the following equation: dCA by dt is equal to minus K1CA, dCB by dt is equal to K1CA minus K2CB, and dCC by dt is equal to K2 into CB. So all are first order reactions. The reactions are carried out in a batch reactor with the respective initial concentration as CA0, CB0 and CC0 respectively. So our first part is for CA0 is equal to 100 and no CB0, CC0, analyze the evaluation of the concentrations. So okay, let's, before writing down the code, let's go to the theory part. Um, from here, Levenspiel. So I guess this part is given in chapter number 10. Just give me a minute. Let's try to find it out. For CHTR, it is given in this way. This is for parallel reactions. Series reactions are also given here. I guess this one, yeah. A2R2S, but this is for continuous stir tank reactor. I guess this is not for batch reactor. Yeah, this we can use. Correct? So see, RA is equal to minus K1 into CA. R is equal to K1 CA minus K2 CR, and RS is equal to K2 into CR. So what do we need to do? First, we solve this equation. So these equations, solution of this equation is minus ln CA by CA0 is equal to K1 into T, or CA is equal to CA0 e raised to minus K1 into T. Now to solve the second equation, it is dCr by dt plus K2 into Cr is equal to K1 into Ca, that is K1 into Ca0 into e raised to minus K1 into so. So this is Bernoulli kind of equation where dy by dx plus py is equal to q, and we need to solve this and we get Cr in this kind of term. Correct? And as Ca0 is equal to Ca plus Cr plus Cs, because Cb0 and Cc0 are 0. So we get Cs is equal to this term. So if K2 is much larger than K1, then equation K2 is much larger than K1. K2 is much larger than K1. So this term will vanish because e raised to minus infinity is 0. So this term will vanish. Then it will be 1. K2 is larger. So we can write K1 minus K2 is equal to approximately minus K2 only. So K2, K2 cancel out. So it is 1 minus e raised to minus K1 T. And if K1 is much larger, then we can write this term will be vanished and it will be 1. Here K1 is larger, so K2 is 0 and minus term minus e raised to minus K2 into T. And from here we can get T max. It is 1 by K log mean, that is ln K2 by K1 divided by K2 minus K1, and CR max by CA0 is equal to K1 by K2 raised to K2 divided by K2 raised K2 by K1 by K2 raised to K2 divided by K2 minus K1. Okay. So this thing we can cross verify further. So let's try to write down our code. Okay. Okay. So let me write down my equations first. So my equation is, sorry. Okay, my reaction is A is to B is to C. Okay. dCA divided by dt is equal to K1 into CA. Correct? Then I will write down my second equation. Okay, let me write it down by my own. Student, just give me a minute. Okay, now I think everything is clear. Okay, so let's write down the second equation, that is d into CB divided by dt is equal to K1 into CA minus K2 into CB. And my third equation is dCC divided by dt is equal to K2 into CB. Okay, so let me do one thing. Let me convert this whole thing. We need to first write down the equations. So let's do one thing. Let's write down a function of, let's say, DC is equal to ODE. I'm just writing it ODE of t comma c. Correct? Now I can write DC of 1 comma 1 is equal to K1 into CA. I write down my second equation, DC of 2 second row first column is equal to K1 into CA minus K2 into CB. Correct? I write down my third equation, DC of 3 comma 1 is equal to K2 into CB. So I need to define what is CA, CB and CC. So CA is equal to C of 1, CB is equal to C of 2, correct? CC is equal to C of 3. Okay. Further, I need to give the values of K1, K2 and K1 and K2. So first, let's take these values. K1 is equal to 2, K2 is equal to 1. K1 is equal to 2, K2 is equal to 1. Correct? So we have given the values of K1 and K2 for this reaction and we have write down our functions. Let's press N. Okay. Now what we need to define? We need to define time. Time is not told to us. So let's take something from 5 t span equal to 0, 5. Then time is we have given. Now I need to give my initial concentration. So C0 is equal to, what is my CA0 is 100, CB0 is 0, CC0 is 0. Correct? Now I will use this function OD45 T comma C is equal to OD45 at the rate OD comma T span comma initial condition C0. And let's see what we are getting. Okay. Okay, what further we can do? I can give TS in some good range. I can do this thing also. So we'll have more number of data points. Okay, 50,001 points we are having. So our plot will be really good. Okay, here I need to write C, not C0. So C, this is the evaluation of CA, then CB and CC. So from here we can't say anything actually. So let's try to um, put it in plot. So first let's write CA is equal to C of all rows and first column. Similarly, CB is equal to C of all rows and second column. And CC is equal to C of all rows and third column. Now I will plot, or further what we can do, instead of writing it like this, we can just directly plot, sorry, T comma C. We can give X label as time, Y label as concentration, and title series reaction. Correct? And then we can give uh, label legend. First legend is my first legend is CA. Second legend is CB. Third legend is CC. Okay, let's try to plot this. Oh, this is something weird. We have made some mistake. It does not look like this. A should decrease and B and C should increase. So we have made some mistake in our code and we'll have to figure it out. Yeah, here it should be minus K1 into CA. This is the issue. It should be minus K1 into CA, correct? Okay, let me correct it here also. So see now, it is showing the correct behavior. So see, from here, you can see that A is decreasing as it should decrease. Now what will happen with B? So A is converting into B. So B is forming, but B is also converting into C. So after some point, B will start reducing. Okay, let me do one thing first. I will write it down in this way only because I want my colors at my convenience. So I will write down CA is equal to C of all rows first column. CB is equal to C of all rows second column. CA with, let's say, it is in color of black with line width of, let's say, it is 1.5. Now I will put hold on. Then again, if you let me copy this part so I don't have to write it down again and again. Okay. It is CA, CB, and CC. Let's say this is blue and this is green. And now let's see what we are getting. So see, here it is very clear that A is reducing with time, B is increasing and C is also increasing. But what was here? Our value of K1 was higher and K2 was lower. Okay, I want to see this. I want to verify this thing from theory. Tmax is equal to ln K2 by K1 divided by K2 minus K1. So let me see first K2. Okay, let me calculate it here only. Tmax is equal to K2 minus K1. Okay, ln. So it is log of K2 by K1 divided by K2 minus K1. Okay, so this Tmax is corresponding to R max. R is my intermediate B. So what I will do, okay. So what is the value of Tmax? Okay, K1, K2, I have not defined it here. I have defined them here. Okay, let's see. Oh yeah, here also I need to give K1, K2. Okay. Yeah. So see, what is the value of, okay, there is some error. Okay, I can write max of CB, not like this. Max of CB. So max of CB is 50. Okay, what is the value of T max? It is 0.6931. Okay, so let's see from here. Okay, I guess from plot it will not be clearly visible. So maximum is somewhere here. Okay, let's try to see from here only. Where did it go? Time. Okay, so 0.6931. What is the maximum value of CB? That is 50. Okay, CB max is somewhere here. Wait, let me check what was the value of CB max. 50. So see somewhere here, it is 50. So which entry is this? So see 50.0040. So it is this entry. Entry number this 6921. So let's see corresponding to 6921, entry number 6921. What is the value of time? Are we getting the same answer? Okay, this is tedious process. We can include directly this in code. Yeah, 6921. So say it is 0.6920. So the theory that we learned is correct. It is no way wrong. Okay. So this is how we can do it. Now we are supposed to change the values of K to, now it is 1 comma 2. So let's do it for 1 comma 2. So both the places I need to change 1 comma 2. And here also 1 comma 2. Kmax will be same, but plot will change. Oh, it has reduced to 25. Okay. So see here, when K2 is faster, so this reaction rate is faster. So we want value of concentration of B won't stay there for longer period of time because B will be suddenly converted to C. Like for the first case, what was that K1 was higher. So uh, this reaction was more occurring A to B. So B was staying for more amount of time. So that concentration was also higher. Okay. So this is what we have seen from here. And the last part is 1 comma 1. So both are same. So I don't know what it is going to look like when both reactions are occurring at same rate. It's same rate constant. I guess we won't get T max from this formula because it is ln 1 minus 1 is on denominator. So we won't get that term. Yeah. Okay. So this is the same plot that we are getting. Okay. There are some quite differences, but C is only increasing. Hmm. Okay. So this was the first part. Now for the second part, what we are told. Analyze the evolution of concentrations A, B, and C. Now we are fixing K1 is equal to 0.99 and K2 is equal to 1.11. Okay, K1 is equal to 0.99 and K2 is equal to, what was the value of K2 is equal to 1.11. Okay. So when we are keeping 100, 0, 0, now what is the condition? It is all we are taking as 10. So our all initial conditions are 10. We are taking everything. So let's see, A should reduce only, B should increase and then reduce, and C should also increase only. But let's see what's happening here. So see here, really a weird plot. A is only, A is black line, so he is only reducing. B is also reducing because B is already there. Are you understanding? A is converting into B, but B is already there. So what is happening? B is getting converted to directly C because our rate constant for reaction 2 is higher. So this is what it is looking like. Okay, let me do one thing. Let me change the K1 and K2. Let me write down K2 here, K1 here. Okay, this thing we can leave, but let's see. So I assume that here we should get some maxima, but I'm not sure what we are going to see. Yeah, we are not seeing the same characteristic is more or less same only because of initial concentration of B. K1. Okay, the next part is CA0 is 50, CB0 is 10, and CC0 is 5. 50, 10, and 5. So our A is maximum, B is minimum, B is less, and C is minimum. So we will get a maxima at B because concentration of A is higher. So B will be formed and then it will be reduced. Correct? So see, A is always supposed to decrease, and C is always supposed to get increase. But A is here first increasing and then decreasing. Okay? This trend is understandable. The last part is 10, 50, and 5. Oh, so what should we expect? A should also, everything should decrease. Only C should increase because K2, C2, CB is really high, so it will already convert our uh, that into C. So see, you can A is reducing, B is also reducing, but C is increasing. I guess you are asked this type of question in your gate examination. So just look 100, right? Yeah. And it was 2 comma 1. Okay, let me save this problem. Okay. So what we learned today in today's class, first we learned how we can solve our uh, differential equations using ODE 15S solver. Followed by that, we learned ODE 23 solver. We learned ODE 45 solver. And we used some series of ordinary differential equations for this purpose. So we solved around 8 to 9 problems where we learned how to define our function for series of ODEs. Okay. Then what we learned one problem statement where in one CSTR, series reactions were occurring. That is, A was converting into B and B was getting converted into C. So this dynamics we learned from first we learned the theory part from the Levenspiel chapter number 3, and this is um, given in this chapter number 3 section irreversible reaction in series where A is converting into R and R is converted to S. And we learned the theory that how CA, CR and CS evolve with time. Okay, then we check this T max and CR max. Okay, and then we took the example problem to solve this series reaction in MATLAB. And for that, we write down our own code for K1 is equal to 2. First, what we did, we write down the function. We write down three differential equations of columns. We gave some values of K1 and K2, correct? Then what did we do? We write down initial T-span, initial conditions, and we used our ODE 45 solver and we solved the equation. Then what did we do? We checked this K1 and we varied the values of K1 and K2 from first to 1, then 1 2 and 1 1. And we saw how this product uh, how this product composition changes with time for CA, CB, and CC. And what did we learn? We learned that A was always reducing, C was always increasing. But for case of B, it was first increasing and then reducing. And then further, what we do? We change the initial composition. When we kept everything same, then A and B was reducing and C was increasing. But when the amount of B was really less, then B was showing some maximum. What we can further do it here, let's say my value of K2 is really high. Let's say it is 100. So let's see what we expect for K2 100. We should not expect any minima, any maxima. See, we are not expecting any maxima of B. B is just reducing, it is converted into C. Okay, so this is how we took so many examples and we learned the concept of chemical reaction engineering, and we tried to convert that part into MATLAB. So thank you for today's session. We will meet next week. So next week we will learn this one more problem that is left for CSTR in series. This one was reactions in series. Now further problem is continuous stir tank reactors in series. So this problem we will learn and then we will go to some boundary value problems. And we will learn those boundary value problems for 1 or 2 further weeks. This was week 7. So week 8 and week 9, we will learn more boundary value problems. So this is all from my side for today. So thank you. And if anyone is having any query regarding to assignment or regarding to MATLAB course, please feel free to write me an email here. I will try to respond as soon as possible. So thank you. We will meet next week.